Thursday, 1:30 to 3, be a team. Okay, my name is Wiswat Property. Okay, office doesn't matter. We're not going to be able to meet maybe towards next semester. Official channels to contact me, 3 ways. One is email, okay, shown here. Number 2 is you can send me a message via the team. That's another official way. And I send you guys the QR code so we can set up a line group. That's kind of like the last resort. So because in the past, when I ask you guys to send me assignments, exams, sometimes Microsoft Team has problem. Okay, that's another ways to do that. Okay, that's kind of like the last resort. Okay, objective of this class is basically when you can read this whole paragraph on your own, but in a nutshell, we're going to study what basically is electrical machines, and then we're going to focus on the DC machines and transformer. Okay, the textbook I put here is electric machinery fundamentals by Stephen Chapman. This is probably the best one out there. University all over the world are using it. Okay, so a few references that I got some materials and examples from that you can check it out if you want to go into this field more in depth. Okay, so your main focus is here, grading. Okay, so we're gonna have assignments in class assignment for about 10%, midterm exam 40%, final exam 50%. Okay, to get a C grade in this class is to have, you need 50%. Okay, no average, nothing like that. Okay, and we have about 15 weeks of class, so these are the topics. Okay, well, we're not going to go into each of them. Hello? Okay, so these are the basic outlines. Okay, now the assignments in the past, it's about 5 to maybe 8. We'll decide as we progress through the semester. If it's a fast pace, maybe. But if here's kind of like the rules. Okay, I post assignments in the assignments tab. You download. I'll stop the presenting. Somebody send me a chat. Okay. And it's in-class assignment. Okay. If you do, you get a pretty good score. You just do it. Don't send me blank paper. Okay. That's the rules of the assignment. So on average, last semester, most people got about 7 or 8 out of 10%. Okay, so these are kind of like a freebie for you guys. Okay, just to help you, but it also part of the practice that you need to do. Okay. Hang on a second. What's happening with? Give me a second. I'm having a problem with my iPad. Okay. And okay. So what we're going to study today is basic stuff first. Okay, electric machine. Let me get a scrap paper. So you have that. It's already in your lecture notes. Okay. So we look at it. What is electrical machines? Okay, electrical machine are, well, first we look at the title of this class first. Okay. Hang on a second, my iPad is out of battery, so it's not readable, right? Okay. So our class is electromechanical. Let me know if it's you know, off screen. Energy conversion. Okay. So we emphasize on this one, electromechanical. These are two words combined into one, electrical plus mechanical. Okay, and the term electromechanical. So here we're basically studying the conversion to energy conversion between electrical and mechanical. Okay, so how you get electrical energy to mechanical or vice versa. Okay, when we talk about the term machines, you know, these are very generalized terms. Anything's a machine, most of it. Our, you know, you and me are a machine, biological machine, right? We have, you know, we consume energy. Bicycle's a machine, you know, automobile or a car's a machine. Okay, so there are many types of machines out there. Our focus is electrical machine. Okay. So what is an electrical machine? It belongs to three, well, sort of, two broad family. Give me a second. So it's machine that relies on this conversion, electrical and mechanical, okay? So our electrical machine, number one, if we do convert from mechanical into electrical, electrical. This is called a generator. So that's by definition. You convert mechanical energy to electrical energy. That's what it's called, okay? The second one, it's the opposite. Electrical energy into mechanical energy. This is called motors, okay? And because both deals with electrical, right? Electrical, you can have DC or AC. So you can have DC generators, AC generators, DC motors, AC motors. Okay. So these are electrical machines. Okay. Although there's a third type that doesn't really relate to the mechanical part of the energy. This one is kind of like special. This is called transformer. Okay. We dedicate one chapter for that. This actually is very important. Okay. We put this as part of electrical machines also. Okay. Why do we do that? Because all three, they operate on the same principle. All this is in the lecture notes already. I'm just trying, you know, explain it so you don't have to worry about, you know, cannot catching up. Just listen and try to understand. That's it. Operate on the same principle. Okay. Which is through magnetic field. Okay, we need magnetic field. as our middleman between the conversion. Okay, so this is what we are focusing on in this class, electrical machines. Okay, now before we do that, we start with the basic. Wait a second, get my notes. Give me a second. Sorry about that. Okay, so in chapter 1, we talk about introduction to machinery principles. Okay, so which is dealing with, electrical machine, its definition that I just described. And then another part of it is a transformer. So that's part of the family. Okay. And then it also talks about these machines that are in your daily life. Okay. Okay. So the question becomes, why is it so common? Why do we see it everywhere? Okay. Well, we see electrical machine everywhere today, which is not really true. We talk about this maybe 200 years ago or 150 years ago. Okay, so the question becomes is, why is electrical machine there? Why are they so common? Okay, so the answer is kind of like, well, I would say it's a trivial answer. Okay, the answer that the textbook gave, which makes sense, but also it's part of the answer. There are many more answers in this. Is that these machines, they're so common. You see a lot of generators. Well, you don't really see it a lot, but you see a lot of motors out there. You see a lot of transformer. If you take note, on the street, especially in Thailand, on the electrical pole. Okay, so you see this everywhere. Why is it so common? Because electrical power or electrical energy is common. Okay, so you have the source of energy or power. So there are plenty of tools using that source, okay? So it's like I ask you questions maybe 150 years ago. Do you see any, well, is that 150? Probably around that time. You want to read something during the night, there's no lamp, there's no, electrical lamp, right? The light bulb doesn't exist back then, 200 years ago. It was invented by Edison, one of the inventor anyway, right? But in order for Edison to sell his light bulb, he has to invent electrical energy that goes along with it, right? So same thing. So because it's there, because the energy is there, okay? A good example for today, if I ask you what is the most common type of car today, automobile. It's mainly fossil fuel, right? Gasoline engine, diesel engine is the most available right now. You see it, the majority of the car on the market today is still, we call that ICE, internal combustion engine, using fossil fuel, okay? If it's maybe, I don't know, 30 years from now, that might not be the case, okay? So the question is, why is the car that we see every day today are so common? The answer would be because oil is common, okay? Crude oil, gasoline, diesel is common. So that's kind of like, well, a good answer, I guess. So we see electrical machine available a lot today in our life is because electrical power or energy is common. Okay, like I asked you today, if you're going to read at night, well, just read books, not your tablets or not your iPhone. You need electric lamp, right? LEDs maybe today, but if I ask you about this maybe 200 years ago, you can't use that. What are you going to use? You can use candle. Okay, we can still use candle today, to see at night, but it's not efficient, right? It's not reliable. It's not really a good way of doing it, right? If the power goes out, what do you guys use? Well, nowadays you would use your smartphone, right? Your smartphone has a flashlight in it, right? Back maybe 10 years ago, 20 years ago, I used a flashlight, okay? And again, unless you have to, you use candle, okay? So the answer lies in, if you have the device, you need some energy that goes along with it. If that energy is, fully available, widely available, there are many tools that's going to be using that source of energy, okay? And that's why maybe in the next 10, 15 years, 20 years from now, all the cars are going towards electrical, okay, electric. There's a term electrify, okay? See, the major car company around the world today are doing electric car, okay, coming out with a brand new model, okay? It's gaining trend, but it's not there yet, but see, so that's why. Okay, now, come back to this. If we ask further, why is electrical energy common? We know now our machine. First, electric machine common. We got the answer to number 2. Electric energy is common. But why is it common now? Okay, there are many reasons for that. Okay. Number one, I guess, well, it's kind of like, again, it's not a really clear-cut answer. Okay, why is electric energy common? Okay, number one, I didn't really go to the order the book says. Okay, it's efficient source. Okay, The best example for this is like, if you compare the efficiency of a car, a diesel engine versus electric car will outweigh that diesel engine counterpart. Okay, electric car, I don't have the number. I'm guessing it's above 50% efficiency. Okay, the reason being is the motor is very efficient machine compared to diesel engine. Diesel engine car maximum efficiency is about 30%. Okay, all the losses, all the waste goes into the form of heat, right? You start diesel engine car for, I don't know, 10 minutes, you touch that, the hood of it, it's going to get really hot. Okay, so it doesn't produce any distance. Okay, so it's efficient source of energy. Okay. Number two, it's, again, this is relative, easy to control. You have this in your notes, okay? If you look at the lecture notes, okay? So you can kind of control electrical machine easier. A good example would be like a heater, maybe. If you live in a cold country, you want to adjust the temperature. If it's electric heater, you can just dial knob to get to certain temperatures, right? But if you don't use heater, you use, let's say, a fireplace. Okay, like you see in the movies for the Thai students, you want to adjust the temperatures. You can't do that easily, right? You want to get it warmer, you put more wood in it to get it burn, more. You want it to get a lower temperature, you take the wood out, sort of. So it's not really easy to do compared to electric heater. See? So it's easy to control. Okay. Number three, it's easy to transmit over long distance. Again, relative term. Okay. Electrical machine or electrical energy or power are generated somewhere else. Not close to your home, very far away, actually, in a power plant. How do you get that energy to you, to me, to everyone else? We do that via transmission line, okay? So these are not really a clear-cut answer. You say easy to control, but you have to build the infrastructure. But if we assume the infrastructure is there already, let's say I want to set up a new power plant and transmit power to Bangkok, I can do that a lot easier because the infrastructure is there. The best example to compare with is maybe a coal mine, okay? You want to let's say I want to use some tool, some device. I can either use a coal to power my device or electric power to do that. To get a coal to your home, maybe you have to dig it from the mine, transmit it, and coal is not light. You got to transmit it over the train. It would take a lot of time to do that. If you transmit electrical power, it's in minutes and seconds to do that, right? So this is part of the deal, okay? And last, but again, this is only true in certain part, it's pollution free, okay? No pollution. Again, to the end user, you and me, okay? Not really true at the power plant, okay? But that's good enough, okay? Again, you're reading a book at night. If you use candle, you get smokes, right? And the light is not steady. If you're using lamp, electrical lamp, it's a lot better. So if you want to do heater, using, fireplace, you get these smokes. Even if it's very little, you still get smokes. Electric heater doesn't generate any pollution, sort of. Okay. So these are some of the main reasons why electric energy is common. Okay. And because this type of energy, electrical energy, is common, electric machine is common. See. So in your future, or at least, in the foreseeing future from now, electrical power is going to rule, okay? We have this, electric car, electric boat, electric train, electric truck, electric chip coming out, okay? And we have this, renewable energy coming out, which produces electrical power with a lot less carbon footprint, okay? All those stuff, more environmentally friendly. So these are our future anyway, okay? So everything is being electrified. So these are the basics. So we have to study some whole concept of it. Okay. We go to the next topic, which is the units. I'll skip that. Our unit is SI unit, which is meter, second, kilograms. Just you know that. Okay. So our next topic is rotational motion. Okay. Because our machine, I think I have a, give me 1 second. We're drawing here. You should have the, I lost my chapter 1 lecture note. Okay. So we have this rotational motion. Newton's law. Isaac Newton's law. And power relationship. Okay, again, I'm just rewriting this. You have this in your notes. Okay. Our machine are not a linear movement machine. Okay. I guess most of you know what is the motor is going to look like. Okay. So I'm going to do a crude drawing here. This is my motor. Cylindrical shape, 3-dimensional drawing with a base. See, it's going to have a shaft sticking out. Kind of like that. See, and this thing's going to spin. So you look at a cross section. This is what I'm going to see, right? So this is a rotational motion. It doesn't move like a linear motion. Okay. So a thing has to be, certain rules has to be set up. Okay, it doesn't move left or right. So we have to define, the directions. Okay. So here, what we do is that we define this. If it's spinning like this, we call this clockwise direction. Okay, the opposite, if it's the other way around, CCW, counterclockwise. Okay, or anti-clockwise. It depends on, certain English they want to speak. Now, how do we tell if you're standing on the back of this or in front of this? It's going to be opposite. So we define this based on the shaft's end. Okay, so you guys, the people has to be standing on this side. Okay, you can't stand here on the back of the machine. If it's very large, you won't see which way it's spinning. So this is our rule, our definition. You look at the shaft and see which way it spins. If it spins like this, like a clock, it's clockwise. If it's the other way, it's counterclockwise. So this is our rule. Okay. So you look at the side where the shaft is. Okay. There are machines that's pretty big, larger than a room, like big generators. If you, standing at the back of it, you won't be able to see which way it's spinning. Okay. So this is, again, if you don't know, this is called a shaft. our machine. You should know that. Okay, it's spinning about an axis of rotation. Okay, so when we understand that in linear motion that you learn in physics, okay, that deals with Newton's, you have a position, which I think is called displacement, right? I think I forgot physics 1 already. Okay, certain textbook gonna use I remember mine uses, I think, a vector S. Okay, so it's distance, a vector quantity. Okay, and then the derivative of position is velocity. Vector V, right? ds by dt. And then acceleration. Okay, A, dv by dt. So again, these are linear motion. We have similar things in rotational motion. Okay, so for us in rotational, okay, we have angular position. You just put like a angular in front of these terms. Okay, so you have this angular position. Okay, and the parameters that we use is theta. Okay, so the ways to measure is that you have to kind of like know what is the axis is. So this is a center of rotation. Okay, and you measure it based on the positive x-axis. So if my position is here, my angular position is this theta. You measure from a reference horizontal line, positive x-axis with the center of rotation. See. Okay. So for example, in a linear motion, I'm trying to do physics here, I'm not sure. This is my original position. I move from this point to that point. This is my S, right? From point 1 to point 2. So that's linear motion. In rotational motion, I will move from point 1 right here to point 2. So I move at certain theta degree, okay, or radians. See, from this point to that point. See, so angular position is measured in degrees or radians. And if you forgot, 180 degrees is equal to pi radians. You got to remember that. Okay. So one rotational movement is 2 pi radians, 360 degrees. Okay. Now, there is a catch. This part, your textbook doesn't really have it, but it's in your notes. Okay. So if I move from point 1 to point 2, I'm moving in counterclockwise. See, right? 1 to 2. If the direction is like that, okay. I call this positive. Okay. But if I'm moving 0.1 down right here to 0.3, I'm moving clockwise direction. I'm calling this negative theta. Okay. So what is useful about this is that I don't need to tell my direction. I can only see the sign of theta. I would know which way I'm moving. Okay. For example, I can move plus 45 degrees. So I would know that I'm spinning in a clockwise direction, 45 degrees. Or I can say I can move negative 30 degrees. That leads to clockwise direction, 30 degrees. You see, I would know the direction based on the sign of this. So positive is associated with clockwise. Okay, you guys didn't send something, right? 1 second. Okay, so the sign of the theta will give you the directions already. Okay. Okay, so this is angular position. Okay, so positive gives you CCW, rotational direction. Negative is CW. Okay, so instead of a linear motion from left to right, you know, up and down, this is the only two directions that we have in an angular position. Okay, next up is angular velocity. Again, symbol that we use is omega. Okay, it's the rate of change of angular position with respect to time, d theta by dt. Okay, the most common units that we know is in radians per second. Okay, very uncommon to express this in degrees per second. It's not very common, so this is the most common one. Okay. Turns out that this angular velocity, there are other forms that you guys are familiar with. Okay. Even, you know, like this one, we're not really used to this radians per second. You know, if they ask you, hey, my motor is spinning at 1 radians per second, you have kind of like no idea. Is that fast or not fast? You have no, I can't, well, even if you ask me 10 radians per second, how's that gonna look? Fast, slow, I don't know. Okay, so the most common for humans, I guess, for regular people, at the angular velocity that we are used to with, and you see this in a dial, in a, what do you call it? The console of a car, the dashboard of a car is revolution per minute, RPM, okay? So I told you, hey, my motor is spinning at 10 RPM. You kind of like have an idea, right? 1 minute is gonna spin 10 loops. So people are familiar with this more compared to radians per second. You see, I tell you, hey, I'm moving 1 radians per second, you have no idea. Unless you're really comfortable with that unit. So it's not really, you know, but here people would know. Most people, regular one would know, right? 1 RPM, 2 RPM, 10 RPM, you know, you have an idea. Okay, So for this RPM, the angular velocity parameters that we use is n's, okay? And usually we have a subscript m. The subscript is for mechanical quantity, mechanical, okay? And this is the one that you can observe because the shaft of the motor is mechanical, okay? So this is also angular velocity, okay? And even more interesting parameters that all of you know already is revolution per second, although you don't really see this a lot, RPS, okay? Another unit for this is hertz. You know that? What is the hertz units of? Frequency, right? This goes to F. So frequency, you know, is also angular velocity, okay, for us in this class. If you learn this, you know, telecommunication, communication course, we don't call that, we just call it frequency. See, unit is hertz. Hertz is some guy's last name who kind of like in honor for him. Okay, so it's Hz, which is also 1 revolution per second. Again, you can have subscript M, or sometimes it's electrical parameter subscript E. Usually without the subscript, by default is electrical parameters. So angular velocity, 3 parameters. Omega, radians per second, n sub m, RPS, I'm sorry, RPM, revolution per minute, and F sub m, hertz. See, you have to know how to convert. Important relationship is we need between these two. How do you convert RPM into radians per second? Okay, how do you do that? So if I say, hey, I'm spinning 1,000 RPM, can you turn that into omega? Okay. How do you do that? Can you do that? Try to go back and practice that at home. Okay. So angular velocity plays an important role. We'll see a little bit later why. Okay. And again, because position we have, velocities that we have, we also have acceleration, but in this class, not really much use of it because most of our study belong under steady state conditions. So there's no acceleration per se, but we just put it here. It's angular velocity. I'm sorry, acceleration. The symbol that we use is alpha, the omega by dt, okay, which is radians per second squared. Okay, again, we don't really use it a lot. Okay. So these are the 3 related parameters. Now, there's one more thing that relates in terms of linear motion. That belongs to Newton's law. If you remember in Newton's law, you have these 3 things, right? And you have this relationship, F equals to ma, right? Force is mass times acceleration. Okay, so we have force in linear motion. In rotational motion, force doesn't really matter much. Okay, what matters more is torque. Okay, so if I kind of like draw a table for analogy between this, I'm going to use scrap paper here. Linear, rotational. So you have position, velocity, acceleration, force, right? So again, this is S, depends on the book, B, A, F. Here would be theta, omega, alpha, related to force. You can think of it as a twisting force. We call this torque. Okay, so torques is an important parameter in rotational motion, so we can have force. Okay. And the symbol that we use is tau, a vector quantity. Okay, let me get a new scrap paper. I got a picture here. Okay, so these are older ones. Okay, now go back to that. Go back to analogy. We know that the force, you know, you go to the physics, you have this object, you put a force into it, you can carry things, right? Okay, but in rotational motion, you can't do that. Okay, so in rotational motion, your torque in scalar is tau, actually it's a vector. This is torque. You can kind of like think of it as a twisting force, sort of. Easier, gives you an easier understanding, sort of. Okay, it's kind of like how you twist the object. Okay, so that means there's some point that you get no torque on a spinning object. Okay, so the book gives you a basic example. Okay, so you have this shaft in the center. If you apply a torque through the center of action here, there is a force here, non-zero, but you get zero torque because the force is going through the line of action, the center. Compared to the same situation, this is center spinning, but your offset, the force, again, non-zero. What you have in this case is non-zero torque, because what's going to happen is that you're going to make this thing spin. You apply a torque into it. So that's kind of like a concept of torque, twisting force. Okay, in this case, your torque has non-zero magnitude. Remember, torque is vector quantity, so it needs a direction. In this case, it's CCW direction, because your object would spin that way. Okay. Torque, this is going to give you a better picture. Okay, so we have an object here, center is there. Okay, I got a force applied here. Okay, before we do that, the official equation, if you've forgotten, your torque is R, vector R cross vector F. Okay, so what is vector R? Vector R is a radius vector. Okay, pointing away from the center. Okay, so in this case, based on this picture, this is your vector R. This is also your vector R. It points away from the center towards the point of action where force is acting on. Okay. So this is the generalized equation. Okay. Our concern is the scalar or the magnitude of this. Okay. So in your book, it's going to say torque is the product of the two. Magnitude of force applied multiplied by perpendicular distance. Okay. So in this case, you get, for example, my perpendicular distance from the center, 0. So my torque here is 0. But if we use the same equation here, this is my perpendicular. If I zoom in this, let's do that. I get a force here. And if I draw this through the line of action, this is my perpendicular distance here. See, from the center. So I know some values here. I know the distance here. I got the magnitude of the torque. Okay, but the more fully covered equation is this one, R cross F. Okay. So this is torque. And if you get that, go back here. I have force in black ink. My radius R. And if I continue with the line of action here, then I would get this between vector R and vector F is theta. Okay. So if I look at this, from that equation, I would get torque is RF sine theta, where theta is an angle between vector F and vector R, right? Now, if you look at this carefully, okay, let's do it here. This is the center. Okay. This is theta. Right? What is the distance here? Do you know? If we know this is R, okay. If I assume this is how would I do this? Cosine, well, I don't want to spend time on this. You can try and figure it out. Why, if this is theta, why this is R sine theta. Okay. You can try to prove that. Okay. I'm giving you a hint. If you know this is theta, this is 180 degrees minus theta. What are this angle? Okay, you can find that out. All right. But again, and that applies RF sine theta. The perpendicular distance here is R sine theta, where, you know, R is the radius. Okay. Okay, so that's torque. Okay. Actually, if you read the book shows you the proof. Okay. Now, back to the Newton's law that we discussed. we have force is m times a in linear motion. So we map the analogy, the table that I just draw right here. Okay, you look at that. F is m times a. So related to F is torque. Something similar to mass in rotational movement, we call that J, alpha. Okay, we're not going to use this because we don't deal with acceleration. Okay, but to get to know the analogy between the two. Okay, so this is how you come up with the equation where J is what we call moments of inertia. You should study this in dynamics or mechanics too. I don't know which class. Okay, but don't worry about it. We're not going to use in this class. But you have to know the range between them. Okay. Okay. Now the important thing is the next two parameters. Okay. We're going to be using a lot. Work. W is yaw parameters. Okay. In linear motion, its definition is W is integration of force through distance. In your book is using R. Okay. Position. Okay. If it's constant force, constant, then what you have is W is F times, sorry, W equals to force times position. See? But we don't deal with linear, we deal with rotational. We use the same mapping. Work is the integration of, instead of force, is torque. This is position, then it's d theta. You see, you map. And again, for constant torque, what do you get? W is tau theta. And this is important for us. Okay. What is work? If we say work, it's not really readily understandable. What's another common name for this thing? What's a unit of work? Do you know what is the units of work? Joules, right? In yes. Joules. And the units in joule, what is that unit for if it's not work?
It's for the energy.
Energy, right. So a more common name for work is actually energy. See, so this is so sometimes when we say work, a lot of people get confused. Okay, energy is more common. Okay, which is the units of energy is joules. You know, or calories for us eating, you know, our meals. Okay, so this is same thing. Work is energy, and we use capital W as our parameters. Units is joules. In short, it's capital J. Again, a guy's last name. Okay. So this is what we actually want to convert energy. Okay. And how do we get energy? We need a torque and its position. Okay. So this is work or energy for rotational movement. Okay. Next, related to energy or work is power. Well, I'm going to be out of time. And the symbol that we use, a parameter we use is capital P. Again, P is very easy. Well, if you know study today in our class, I kind of like speak mix between power and energy, between the two. They're not the same. Okay, especially in Thai words, they're kind of like they get mixed up, okay? But basically, power is how much energy for a given time, dW by dt, okay? So it's a unit of work per unit of time, okay? So this is definition of power, okay? So if we do this, this is the definition, okay? So it is energy or work per unit time, seconds usually. So it's joules per second. See, and we don't call it like that. We have a more common joules per second. We honor a person again. This is also watts. That's the units of power. And that's what you see a lot, right? You're charging your phone charger is about, if it's the old models, 10 watts. Now it's like what, 20 watts, 30 watts, right? That's the amount of, energy per second. Okay, and again, the symbol that we use is capital W. Okay, and if you do this definition, if it's linear, okay, for constant, again, for constant values of force, you're going to get P is D and W is F times R, right? By dt. You're going to get F dr by dt. This is velocity. So in linear world, power is F times V. Okay, but that's not our concern. Our concern is rotational. Let me finish this up. Again, we repeat that. P is D torque theta by dt. So it's tau d theta by dt. And again, here, this is omega. So your concern is power is equal to tau omega. So this is an important equation for us. So that means if I know, let's say the amount of power that my motor, output is, I know the rate of rotation and can calculate the torque, or the other way around. If I know the rate of rotation, I know how much torque and can calculate the amount of power for a given motors usually. See, so this is the power relationship within the rotational world. Okay. So I think that wraps up the basic stuff. Okay. More importantly, so we know that the units of powers are either watts. Another common unit is horsepower. Okay. HP. And we know that 746 watt is equal to 1 horsepower. You have to remember that. Okay. These are very common industrial names. Okay, 1 horsepower motor, fractional horsepower motor, that kind of stuff. Okay. So I'll stop with basic stuff here today. So this is just a preliminary, understanding that the rules that's going to be for us throughout the semester. Okay, I'll stop here for today. I'll see you guys again on Thursday. A little bit, clumsy today. My iPad is acting out. Anyway, so next time we're actually going to go to the main topics of this class. So we study what is a magnetic field. Okay. I guess I'm out of time, right? Yeah. So any questions right now? You can send me a chat message later if you have a hard time understanding what I talk about, my handwriting, stuff like that. But all this handwriting, it's already in the lecture notes. Okay. All right. Any questions?
No, sir. Thank you for today. See you.
All right.
For this class.
If there's nothing else, I'll see you on Thursday. All right.
Thank you, sir.
Thank you, sir.
Don't forget to join the line group. I send you guys a QR code. Okay. So join that group, and then probably next week I'll start to make up the list of who's who. All right. All right. Bye.
Ajahn,
Yeah.
Ajahn, can you take a picture of the writing lecture notes on this class to the files again? Because sometimes it's blur on the camera. So like
But
the
you have
recording.
this already. It's in note 1. More,
all right.
a more type ready picture. This I'm just re-explaining to this.
Okay, thank you.
Okay. I'm rewriting all the lecture note 1-1.
Thank you, Ajahn.
Bye.